Hello, welcome back. Today we want to talk about the aurora that exists in the northern and the southern hemisphere and try to understand what they are and how they work. So the aurora that we see in the northern hemisphere is called the Aurora Borealis, and the aurora that we see in the southern hemisphere is called the Aurora Australis. So it's not going to be just a series of pretty pictures. What I really want to do is talk about what is an aurora, how do they work, how do they occur, and more specifically, what is the physics that kind of surrounds and explains the aurora. Because if you understand how the aurora works, which is this beautiful light show, then we're going to talk a little bit about how that same principle is actually being applied to nuclear fusion research, because it all involves magnetic fields, it involves plasmas that are coming from the sun, and these particles get trapped in this magnetic field, and it turns out that's exactly how we're traveling down the road to nuclear fusion. So there's a lot of goodies in here. We're going to talk about the magnetic force along the way. Join me as we talk how do the auroras work. So before we talk about the math, let's just take a minute to look at what the aurora actually is. Here's a video from Iceland, and you can see that the aurora are these beautiful shimmering tendrils, mostly green, but sometimes other colors as well, and they kind of like meander across the landscape. And if you watch these high-speed time-lapse situations, you can see them moving with great wave-like characteristics and patterns. So they're not a very static thing, they move around quite a bit. Now here's another aurora. This one was filmed over Norway, and you can see that, again, this is a wispy green display of light, and this one has kind of a hint of blue. If you look carefully, you can see hints of blue. So most of the aurora that we see are predominantly green, but with hints of blue. We'll talk about why a little bit later. Now, here is an aurora taken from orbit. You can see these things from space as well, and you can just see how beautiful it looks to be looking down from above. When you see it from orbit, you can actually see that the extent of these things is massive. These are huge structures that traverse the surface of the planet. Now here is a still image of an aurora taken again from above, from the International Space Station. Again, mostly green, hints of blue, occasional hints of red. Now here's another picture of an aurora, again taken from the International Space Station. This one I picked specifically because it shows that when you look at the aurora from space, you can see hints of pink as well. And we're going to talk about why in a little bit. When you look from the ground, you don't see so much of the pink, but from orbit, from above, you can actually see pink light as well. And here's another image, it's just you can't get enough of these things. They're just absolutely stunning, again, from the International Space Station. You can just see how these things are spread over such a wide distance. And you might put yourself back in prehistoric times, when you would look up at these things and just be completely captivated by something you just do not understand at all. Now, let's move away from Earth. Earth is not the only planet that has aurora. We have taken photos and videos of aurora around other planets as well. So here is a wide shot of the entire planet Jupiter, and you can see the aurora near the North Pole of Jupiter there. Here is a close-up of the aurora on Jupiter. You can kind of get in a little tighter. You can see that there's circular nature. The greatest intensity is in a circular region. So it isn't just like a static thing. It's a circular annulus, sort of. And we'll talk about why as we get into the details here in a little bit. Now, if you put these things together, you can look at this composite movie of Jupiter. As it is turning, you can see the aurora there and sort of the scale of it as Jupiter is rotating. I just can't even imagine seeing this with your own eyes. It's absolutely stunning. And here is a image from the Hubble Space Telescope of Saturn. So we've seen auroras around Saturn as well. We can see the aurora there at the pole of Saturn. And here's another picture of Saturn from the Hubble Space Telescope where we can see the aurora visible. Now, I wanted to lead with the pictures because the pictures are absolutely stunning, right? So when you look at it, it just shimmers and moves. It's almost mystical. It's almost magical, ethereal, whatever word you want to put on it. It's unlike anything we really see in everyday life, right? So what is the aurora? Obviously, it's the display of light we're talking about, right? They occur from about 100 kilometers above the surface up to about 300 kilometers above the surface. We'll talk about why. Well, the reason is because it's an interaction between the solar wind of the sun with our atmosphere and our magnetic field. And so essentially what's happening is the sun is sending out plasma from the nuclear reactions happening. It expels this plasma out. We'll talk about what that means in a minute. And when it hits our magnetic field, it gets trapped and it ends up hitting our atmosphere and creating this light show. Now, why does it only happen around the North Pole and the South Pole? Or why is it more intense there? Why doesn't it happen around the equator? Why does it the colors why isn't it like purple? Why isn't it like yellow? Why is it always green? I mean, those are questions we'll answer, but that's the general idea. The different colors we see are interaction with different gases. You know, oxygen, nitrogen, but also normally oxygen is O2 and nitrogen is N2, right, as a molecule. But in the upper atmosphere, there's enough energy where oxygen can exist as a single atom and not just a molecule. So the colors you get out of the interactions are different with oxygen that's just a single atom versus when it's a molecule. And so we have lots of different color mixing that can happen with auroras. All right, so we want to go a little bit deeper. So I'm going to draw a quick little picture, and we're going to explain exactly how this happened. And by the way, we're going to get deep into the magnetic forces. I want you to understand exactly how the solar wind gets trapped in the magnetic field. How does it happen? Why does it get trapped? It's not enough for us to say, oh, magnets attract. That's not sufficient. We need to know why it happens. Why? Well, maybe we'll take this and build a nuclear reactor out of this process, right? So let's understand it together. So we have this big nuclear furnace in the sky. We call it the sun. Now, this is not a lecture on nuclear fusion, but you know that the sun is fusing hydrogen into heavier elements, notably helium, and the helium is fusing into heavier elements and so on. So there's lots of different reactions here, predominantly hydrogen fusing into helium. There's a lot of details there we'll talk about a different day. But as part of that, the sun has its own extremely powerful magnetic field. And if you look at images of our solar telescopes, you can see these enormous solar flares just coming off of the surface of the sun. And in that process, the sun is constantly spewing out and sort of belching out what we call the solar wind. The solar wind is another name for plasma. That's just streaming away from the sun. Now, I've done a whole lesson on what plasma is, but just to refresh your memory, we have a neutral atom of helium, let's say. It has an equal number of protons and electrons, so it's a neutral atom. But in the sun, everything, all the electrons are ripped apart because it's so hot, and so you have a plasma. Plasma just means that the electrons are missing and removed from the atom. So you have charged electrons and charged nuclei, maybe helium nuclei, or maybe even just a single proton by itself, which is a hydrogen nuclei. And so you have all of this stuff not existing as an atom, but separated. We call that a plasma. So it's like a charged fluid. We call it a solar wind. And that is streaming out from the sun. It is going in all directions, of course, but I'm drawing it as a straight line this way because over here, I'm going to draw our friendly neighborhood planet Earth. And so, of course, it's going to hit the planet Earth. Now, what is coming out from the sun? It would be too exhaustive to list, but we have protons, which are coming and streaming out from the sun. We have electrons, which are streaming out from the sun. And we have other ions, meaning there could be helium ions, which would be like two protons together, maybe with some neutrons, but again, a charged ion flying away from the sun. Maybe even heavier ions flying away from the sun. But predominantly, it's almost all protons and electrons just streaming out from the sun. That's what the solar wind is. Now, you may have heard that our Earth has a nice, wonderful feature built into it. It's called a magnetic field. So what we have is a magnetic field surrounding the Earth like this. Now, this is a two-dimensional picture, but if you can visualize it in 3 dimensions, then you can envision like a torus surrounding the Earth in all directions like this. So magnetic fields have directions, so I'm going to draw these little arrows. I'll draw one little loop like this. And what happens is the farther away it gets from the Earth, you see how the spacing of the lines gets farther away? Maybe if I were to draw one more, it'd be even farther away like this. And the farther and more separated the lines really are, the weaker the intensity of the magnetic field. So as you get farther away from the Earth, the magnetic field is weaker. So the closer those magnetic field lines, the stronger we say the magnetic field is. If you want to learn a new word of the day, maybe you already know it, that's fine. But for those of you who don't, the word flux, that's the word of the day. When you talk about flux or flux density, it's how close these lines are together. Higher flux density just means lots and lots of magnetic field lines in a region of space. So this is low flux density, this is high flux density over here. And over here at the poles, notice it's the highest concentration of flux density because all the magnetic field lines, they meet and join at the poles. And so if you had some goggles you could put on, you would see a higher flux density of the magnetic field near the poles of the Earth. That is a very important part of why auroras happen. Notice they happen near the poles. Notice the magnetic field is strongest at the poles. So that's going to become important in a second. All right. Now, we can give the lower level explanation of why the auroras happen here in just a few words. What's going on is the sun is spewing out plasma, protons, electrons, and other ions in all directions, and they eventually collide with the Earth. But because the protons and the electrons and the ions are all charged, they get trapped inside of the magnetic field of the Earth. Now, that's, like I said, the lower level explanation. You can just believe me, they get trapped in there, and that causes the aurora. What ends up happening, they get trapped in here and they start bouncing back and forth between the poles. An electron or an ion might travel from the North Pole all the way along a field line to the South Pole, maybe in a few seconds. Now think about that. That's thousands of kilometers that it might travel in a few seconds. And then it might bounce back thousands of kilometers the other way, thousands of kilometers the other way. And so they get trapped in here, bouncing back and forth all the way around the planet. And when they come and they enter into the atmosphere of the North Pole, see, there's no atmosphere over here, but when they get close to the poles of the Earth, they interact with the atmosphere. And they start colliding, literally colliding with the gas molecules that we have in our atmosphere. And that generates light. Much in the same way that a neon tube is a gas, but in that case we put electricity into it to make the electrons jump up and then fall back down, and they emit photon of light and they glow in that way. What's going on with the aurora is essentially a gigantic version of that. We have a gas, which is the Earth's atmosphere, and instead of electricity, we just have energy coming from the sun, from the solar wind. When the particles get trapped and they bounce and they hit the poles, they are literally colliding with the gas molecules. And so the electrons of our atmosphere are going up to a higher orbit and falling down. And when an electron decays in orbit, it releases a photon. And so that's what's happening. That's why they mostly happen around the northern and the southern pole. That's why they occur much less frequently as you go down towards the equator, because the magnetic field is not as concentrated here. And so there's not as much plasma being well, the plasma is not really being trapped here. It's just traveling to the other pole. The collisions with the gas are happening over there. Now, that's sufficient to understand what causes the aurora. But I don't want to stop there. That's just leaving the fun part out. I want to understand and talk to you about why it happens. And can we use this idea or this physical phenomena to trap plasma for other purposes like a nuclear reaction? And this is what we're doing all around the world here. All right, so let's talk about a little bit about the colors of the aurora before we discuss the physics of how it gets trapped. In the pictures we saw, there were, from orbit, there were reddish colors. These red colors were mostly taken from the orbit of spacecraft like the International Space Station. But from the ground, we mostly see green colors shimmering, but we also see the occasional blue. Blue is much more rare. It's almost always green in color, but you do see reddish when you look from space. So I want to talk a little bit about what causes these colors, what the difference is between the colors, right? So as you go up in the atmosphere, you see we start from the ground. We know the atmosphere is mostly nitrogen, but that nitrogen is as a molecule into gas. And the oxygen that we breathe is O2 gas. Oxygen energetically wants to bond with itself to make a molecule of oxygen. We call it O2 gas. It's not a single atom, it's two of them joined together. That's what we breathe, right? But when you get to the upper atmosphere, this oxygen is no longer bonded to itself. It's called atomic oxygen. When you see atomic oxygen, that's just a single oxygen atom off by itself, not bonded to another oxygen atom. And it turns out that the electrons surrounding a single oxygen atom are able to be excited, and we'll talk about exciting them and making the photons in a minute, in such a way that the frequency that comes out of atomic oxygen when it's pummeled by this solar wind is a reddish color. And that's why we only see the reddish color of the aurora from space, because only at the higher elevations of the atmosphere can the oxygen molecule be broken apart. And the reason it's broken apart also is because of the solar wind and radiation that's up there. There's enough energy to break apart the oxygen molecule to exist like that. So that's why we don't see red from the ground. We only see it from space, because atomic oxygen really is only in the upper atmosphere. Now, we almost always see greenish colors. Now, there is a transition in atomic oxygen that yields a greenish color, but it's predominantly the nitrogen molecule. Remember, we said that nitrogen also, which we breathe, our body doesn't really use it, but we breathe it in. It's not just nitrogen atom by itself, it's bonded to another nitrogen atom. We call it the N2 molecule. And there's a transition of electrons in this molecule that gives a predominantly green color. And this is the one that's excited the most often by the solar wind. So when you look at the green color, you're mostly looking at the light coming out of nitrogen molecules in our atmosphere. Now, lower down, we do have some blue, but it's rare. It's very rare. You need a lot of energy from the solar wind to trigger the blue transition. And this is mostly the N2 molecule. We say, well, wait a minute, there's N2 here and here. Well, it's because you need a lot of energy to trigger the blue photon there. So you don't see that one as often. So we have a reddish color, greenish color, bluish color, but it's predominantly a mixture between green and a little bit of blue, and that's mostly what we see. Now, when we say we trigger a photon to be released, what do we mean? All photons that you see, that go into your eyes that you actually see, they're basically all generated by matter, somewhere. I want you to think about this for a second. When you turn the light bulb on, the photons you see are coming out of matter, the light bulb in the matter. If you see a neon tube glowing, you're seeing the photons coming out of the gas or the plasma. It's coming from matter. When you look at the sun, those photons are generated in the nuclear reactions of the sun. They're coming from matter. If you take a piece of metal and put it in a campfire, and so you have a red hot poker and it's glowing red, the glowing red light is coming from matter. I can go on and on. When you look at from the mirror, the light hits the mirror, it vibrates the atoms there, it bounces off, and you're seeing light reflected off of matter. But any source that you name, it's going to be coming from some sort of matter, somewhere, either from stars, from glowing matter. Even me, I'm glowing in the infrared frequencies right now. I'm generating photons. So matter and energy are intimately related, okay? And so the same thing is true of the aurora. The light that we see is coming from matter, but how does matter, quote unquote, generate photons? Well, it comes from electrons jumping up and down in their orbits. That's pretty much all of the matter, all of the photons that we see are coming from there. Or in the case of the sun, it's coming directly from the nuclear reactions between the ions. But in most everyday life, even a campfire, when you're burning it, the light is coming from matter. It's coming from electrons jumping around from the burning process. So this is not a chemistry class, but we'll just talk about the concept of an atom real quick. And there's a nucleus here, so I'll write down nucleus. Now the nucleus, remember, has protons and neutrons, but it doesn't matter for our discussion, so I'm just going to label it nucleus. Now surrounding the nucleus is a bunch of electrons. Now this is a cartoon. Please, please do not write to me and say, well, your picture of the atom was wrong. It's not really like that. Yeah, I know it's wrong. But you know, if you want to dive into quantum mechanics, then we have to talk about the Schrodinger wave equation, and we have to talk about, advanced math and things like that, which kind of like are beside the point. Just for sake of argument, visualize a nucleus, which is a positive charges, protons and the neutrons. Surrounding that is a cloud of electrons. The electrons are not really balls like this. They're really waves, but it's okay. You can still visualize them as little balls for the sake of discussing something, okay? And they're some distance away. Now they're not orbiting like a solar system. They're not a fixed distance away. And so the picture is actually completely wrong, but it still lets us visualize one of these electrons when it receives energy from, for instance, the solar wind. So we say maybe the solar wind, let's see, I'll put it like this. The solar wind comes in. Right? A proton or electron comes in from the sun, and it hits one of these electrons, and this electron gets kicked up, this is an electron here, into a higher orbit, which is now kind of farther away. Now, again, it doesn't really get kicked up. It's not a ball that goes to a higher orbit. It's a wave. It's a probability wave. But still, you can visualize it as going into a higher orbit, which implies higher energy. Where did the energy come from to kick it up here? Well, it came from the solar wind, from the nuclear reactions in the sun. That's where the energy went, so you're not getting anything for free. But this electron, when it is in this higher state, see, there's a vacancy down here now. And so the nucleus is going to attract it right back down. And so this is going to come, So there's a vacancy, right? And it's going to come down, well, you might think it go down to the same place, but for this diagram, I'm just going to draw it coming right back down here. And whenever you have an electron going from a high energy to a low energy state, it releases a photon of light. So you're not getting free energy. All that's happening is you're taking the energy from the solar wind, which comes from the nuclear reactions, protons and electrons hitting an electron. That energy kicks it into a higher energy state. That's where the energy went. But as soon as it's in there for any length of time, there's a vacancy here, and the nucleus is going to pull it right back down here. So when you go from high energy to low energy, the energy has to go somewhere. Conservation of energy. And when it drops down, the only place the energy can go is to be shot out like a photon. So literally, you're taking energy from the sun, from the energy of the solar wind, and you're converting it into photons, which we see. The atoms are doing that, the atoms of our atmosphere. All right, so we basically covered at a high level how the aurora actually happens. We said the solar wind is belching out particles constantly. We said that there is a trapping going on there between the north and the south pole. Somehow the magnetic field traps the particles. And when the particles collide with the atmosphere, they're kicking up electrons. The electrons are decaying and they're releasing photons. And the different color of the photons are coming from the different types of gases that exist at the different altitudes of our atmosphere. So that is a very good introduction. But we don't want an introduction. We want to go deeper. We want to understand more fundamentally, how does it get trapped? How does it work? Because I actually think that's the most fascinating thing, part of the whole thing. And also has applications in not only fusion, which I've mentioned a few times, but also propulsion systems for deep space. I actually worked on one of those for several years and, in graduate school. And so I know a fair amount about propulsion systems involving plasma. So I like to share some of these things with you here. And essentially, if you understand the aurora, then you can understand how any of these things work because they're all the same principle. So what we need to do is draw a little bit of a bigger picture, right? We need to draw a little bit of a bigger picture. So up here, I'm going to draw the same cartoon that I drew below. So this is the Earth, right? And I'm going to draw it a little bit bigger just so that we have something a little bit more to talk, a little bit easier to talk about. So here's some magnetic field lines. And notice that as I kind of draw them out here, I'm going to try to space them a little bit farther out. And remember, when they're spaced a little farther out, that means, whoops, that was a terrible one. Sorry about that. That was a little too far out. For symmetry, it needs to be probably more like this, something like that. It's just a cartoon, okay? Don't get too wrapped up in it, right? These have a direction associated with it, so we'll draw a little direction right here, right? And I'll do a whole video one day on why the Earth has a magnetic field. There's actually a lot of research into it. We know generally how it works. The details, the minute details are where people are still studying things. But it comes from the molten core of the Earth, and we have multiple layers in the core rotating past each other, and it sort of behaves almost like a generator or a charged particles moving, which create the magnetic field there. All right, so what we have here is the solar wind streaming in, and the solar wind comes in, and we have electrons and protons which collide. We have electrons coming in here, and we have protons coming in here, and they're colliding with this thing, and they essentially get trapped here. So I'll draw one right there, and put an electron there, and put a little proton right there, and they literally get trapped, and they start bouncing back and forth. Why do they do that? We're going to talk about that in just a second. Now, in order to visualize it a little bit more, I'm going to do my best to draw a little bit of a better picture from an angle. So let's try to draw it. I'm not a great artist, so please forgive me, but I'm going to try to draw a perspective looking down, if you were looking down at the North Pole, right? So I'm going to try to do that. So I'm going to draw it down here. Let's draw this, and we'll draw something like this here. So this is the North Pole right here. If you could visualize it, something like this. This is the magnetic pole of the Earth. All right, now what do we have is we have the magnetic field coming out of the pole. Now I'm not gonna, the pole, it actually enters the Earth and goes down inside, so it doesn't actually go directly into the pole right here. There's a little bit of an angle there like this. And so what I'm gonna do is sort of draw it coming in something like this. It goes around, and there's this one there, and then there's one over here. Like I'm trying to draw like a little bit of an angle right here, and then maybe one up here, can go like there and kind of going around, wrapping around over here. And then over here, let's see where I can draw this one. It'd be something like this. And then there's one right here going around like this. So you have to use your imagination because I'm not a great artist, as I've said about 10 times, but you get the idea. You have these arrows like this. And so when you look at it from the side, yes, you can cleanly draw these donuts, but from an angle, what you have here is you have them entering the North Pole like this, and then they curve around into the South Pole like this. And what you actually have are these particles, which are electrons and protons from the sun, which are essentially trapped. Now, when I say trapped in the magnetic field, what actually happens, and I'm going to talk why in just a minute, the protons and electrons from the solar wind, when we say they're trapped, they're tightly orbiting along the magnetic field lines. I'm going to say that again. They are tightly orbiting along the magnetic field lines. They're free to move along the magnetic field, no problem, but they're tightly attached, so to speak, or orbiting around the magnetic field lines. This is why they're trapped. So you might have something like this, where this is like orbiting this direction. It's spiraling and it can move along the line freely, but it's tightly coupled in one direction. It can't get away from the field. It can move along the field, but it can't get away from it in a perpendicular direction. Maybe another one right here, right? And then you can see that because it can't get away, but it can freely slide along the magnetic field, that eventually it's going to collide with the atmosphere in the North Pole. Maybe it'll bounce off of the magnetic field that's here and then do the same thing here, back and forth, back and forth, back and forth, colliding with the air molecules when it gets close to one of the poles. Now here's where I use one of my props, and it's not the best prop, but basically this is an Earth, and of course the Earth is at an angle. And by the way, the North Pole of the Earth is not the exact same location as the magnetic North Pole. They're a few degrees apart, right? So, but you can still point to this and say it's pretty close to the magnetic pole. So what's happening is these magnetic field lines are coming out of the pole, they're traveling this direction, and then they go into the pole down here. And this is happening all the way around the planet. So it's like a torus or a donut, if you want to think of it, going all the way around. The particles that come from the solar wind, I'm going to explain why in just a second, but they're trapped along these magnetic field lines. They are spiraling, literally, if my fingertip here is a particle, they are spiraling along the magnetic field lines. In other words, they can't get to the left or perpendicular from the field very far. So they're trapped in that direction, but they're not trapped along the magnetic line itself. So they can spiral along like this. As long as they're trapped along the field line, that's what the magnetic force is doing. It's trapping them from getting away from the field line, but so they're only trapped in one direction is what I'm trying to say. So when something is only trapped in one direction, then it's going to spiral because it can move along the field, no problem. Now I have another prop to show you that. Let me put this down and I'll show you something else. I want you to visualize the solar wind or the magnetic field, I want you to visualize it as this piece of string. Is the magnetic field really a string? Of course not, but you can visualize it. Now this black particle there, you can kind of see I can like flip it around and make it sort of orbit like this. The field itself isn't moving, but the particle itself is orbiting in literally in a circular pattern, but it's still allowed to move along the field line, right? So I can freely have these particles move along the magnetic field line, but they are trapped in a direction perpendicular to a field. So I want you to visualize the solar wind trapped in a magnetic field, in any magnetic field, in a nuclear reactor or in a plasma propulsion rocket or anything. If there's a magnetic field and a plasma, the plasma is trapped orbiting the magnetic field lines. Now, what we have to do next is talk about why are these particles orbiting the magnetic field lines? How does the trapping happen? Because I think that is the most fascinating thing about all of this. All right, here's where we take the kid gloves off. We have to do a little more. There's only so far I can go, otherwise you just have to believe everything I'm saying. What we have determined over the years is that the magnetic force follows the following form. The force from the magnetic field, B is what we use to represent the magnetic field in physics and engineering, right? The force is a vector from the magnetic field, and it's equal to the following. Whatever the charge is, that affects the magnetic force. The charge meaning whatever is orbiting the field line, electron and proton, multiplied by the velocity of the particle and the magnetic field intensity. But the operation here is a cross product of two vectors. Now I know that this x looks like multiplication. I know that this x looks like multiplication from 4th grade, but it's not multiplication. When you have two vectors, there's actually lots of ways you can multiply them together. And so this way is called a cross product. And actually there's lots of examples of cross product, not just magnetic fields. When you look at the torque that you exert on a torque wrench, the torque is what we call in physics a cross product between the force that you're exerting at the end of the torque wrench and the distance from the pivot point, right? So those are like two little directions, and you all know from everyday life that the longer the wrench, the more torque you have, right? You also know that the angle, it's better if it's 90 degrees. If you have a long wrench, it doesn't do any good to push towards or away from the pivot point. You have to go 90 degrees to get the most torque. So the torque is a cross product, and the torque being a cross product just takes into account the length of the two vectors and the angle between them. For a torque wrench, 90 degrees gives the most value of the torque. And so here we're going to learn in a second that the magnetic force is biggest when the velocity of the particle and the magnetic field direction is 90 degrees to each other. I'm going to get there. Just hang on, let me draw a few pictures. All right, so this thing is called the magnetic force. This is the force on a particle moving in a magnetic field. This is the charge on the particle, electron or proton, plus or minus 1. This is the velocity of the particle. And this is the magnetic field strength. And the units of that is in Tesla. You may have heard of the word Tesla, right? So this is the force that a magnetic field pushes on a charged particle. If we understand how the magnetic field works, then we're going to quickly figure out that these particles orbit inside of the magnetic field. And that's all I'm trying to get across to you. I know it's a little bit to take in the beginning, here all at the same time, but I promise, just go through a few diagrams with me. It'll be worth your time. I promise you this. All right? Now, just like the torque wrench example, what this equation is really telling you is the magnetic force is actually perpendicular to the velocity the particle is moving and the magnetic field that the particle is in. Now, I just wrote it down because I'm going to come to it later. Because when the force is perpendicular to these two things, that's what the cross product does. That is going to lead to the orbiting motion of these things. So let me draw a picture and we will understand it together. Let's say that I have a magnetic field which is this direction. It's a constant uniform magnetic field, so I'm just going to draw a few magnetic field lines. Notice they're evenly spaced, so there's no bunching up. It's a constant uniform magnetic field in this region right here, right? And inside of this region, I'm going to draw it between these two field lines right here. I have a particle moving with some velocity v. I'm sorry. So the magnetic field has some magnetic field strength, right? And this velocity is a vector also, so I'll put the velocity as an arrow as well. Now the magnetic force acting on this particle is given by this equation. It's the multiplication of three things. The charge on the particle, because it's going to be an electron or a proton in this case. It could be any charged particle, even an ion, but let's just think of it as an electron or a proton. So this is going to be plus or minus 1, multiplied by the velocity of the particle, multiplied by the magnetic field strength. However, this cross product adds something else. The cross product involves the angle between them, right? So what's basically going on here, let me go ahead and pull up my prop here. What's going on here is I have two little props. This one says B, and it's oriented in the direction here, and this one says V. So this is the direction of the magnetic field, and this one is the direction of the particle. When the magnetic field is oriented like this, and the particle is moving along, in other words, it's not going up or down from the magnetic field, exactly parallel to the magnetic field, then it's Q times V cross B, right? And what you do is you take the right-hand rule in order to figure out the direction of the force. But the problem is, the way the right-hand rule works is you only get an answer if there's an angle between them. You see, if I take V cross B, this is V cross B, the right-hand rule is telling me I put the vectors tail to tail, and I take the V vector and I curl it with my fingers into the B vector, that's V cross B, and the thumb would mean that the force on this particle would be pushing into the board, which means it would be deflected this direction into the board, okay? And as I make the angle smaller, then I still cross V cross B, but because the angle is smaller, the force is still into the board, but it's less of a force. When the angle is smaller, still, the force into the board is smaller. When the angle is 0, the force is technically into the board, but the magnitude of it is 0. The cross product of two vectors takes into account the directions and gives you an answer perpendicular to the two vectors that you started with. Notice the force is perpendicular to these vectors, but you're going to get more of a force, just like a torque wrench, if you're pulling 90 degrees or pushing 90 degrees far, far away, you're going to get the most torque. Think about it like this. If you're doing a torque, you're going to be able to do a torque wrench with a lot more torque like this, but if I'm pulling at a weird angle like this, it's not going to be as much torque. So that's graphically what's going on, but the cross product, F, is Q V cross B. All right, when you write it down mathematically, the magnitude of this force is Q times V times B times the sine of the angle between them. This cross product turns into, again, I told you, multiplying them together, the magnitudes of them, I guess Q and then V and then B, the absolute value bars mean I'm just taking the magnitude, times the sine of the angle between them. But look at this. If the particle is in the same direction as the field, the magnetic field, what is the angle between them? The angle between them is 0 in that case. And so sine of 0 degrees is just 0. So the magnetic force is just going to be equal to 0. If the particle is traveling exactly in the same direction of the magnetic field, there's no magnetic force. You see, people think that magnets just attract things, but they don't. They only have a magnetic force if the particle is moving, but not only that, it has to be moving with some perpendicular nature to the magnetic field itself. If the particle is moving exactly in the direction of the magnetic field, there is no force. There's no force from the magnetic field at all. And it comes back to that cross product. It's Q times V times B, the velocity of the particle times the field strength times either plus or minus 1 if it's a proton or an electron, but times the sine of the angle between them. And if the angle between them is 0, there's nothing there. And so you can replicate this with the cross product. I told you it's going to be V cross B. That means that this cross product makes a maximum force when the angle is 90 degrees, because then it would be sine of 90 degrees, and the force would be into the board. As the angle gets smaller, the sine of the angle gets smaller, and the magnetic field gets smaller. Eventually, if the particle and the field are exactly lined up, then the sine of the angle is 0, and technically you cross them, but there's no result because there is no angle between them, and there's no magnetic force in that case. Now, let's go to the case that makes all the difference. This is what we really need to talk about. We have the case of a magnetic field, B, into the board. If the magnetic field is into the board, what would that look like? I'm going to represent the magnetic field with X's. This is pretty common with vectors. If you see X's, it means the arrows of the magnetic field are going into the board. So you need to visualize this first. What I mean by into the board is this arrow is the direction of my magnetic field. It was this way here, but the X's are like the tail of an arrow or something, and so the arrow here is now going into the board, and the X that you see is like the tail feathers, right? If it's coming out of the board, it would be totally opposite of this, going into the board. So every X here is a magnetic field going into the board as oriented by my little prop right here. All right, now let's say that I have a particle in this magnetic field right here, put the particle right there, and the particle's velocity initially is V in this direction. What is going to happen to this particle when it's in this magnetic field? Well, it's going to be Q times V cross B. And so it's QVB sine of theta, but forget about the sine of theta. Just say, okay, this is a magnetic field. Magnetic field's going into the board. And the velocity, this is my velocity of the particle. I'm going to turn it around this way to match what I have. You put them tail to tail, and you have the magnetic field into the board. You have the velocity of the particle down here. And then what you do, if I can grab them, this is difficult. I'll hold it like this. V cross B, it's QV cross B. So you take your fingers, you cut into V, then you cut into B, and my thumb is pointing down. So when the field is oriented like this, there's 90 degrees between them, 90 degrees between the field and the velocity of the particle. I cut in and I have a force down on this particle, which means the particle what am I going to use? The particle has a force acting down on it. I wish I didn't use blue. Here's my magical black pen. It means the force is acting down perpendicular in this direction. Notice I said the magnetic force is perpendicular to the velocity of the particle and the magnetic field. If the velocity, and this is always true, if the magnetic field is into the board, right, and the velocity of the particle is right here, and the magnetic force is acting down, notice that it is 90 degrees to the magnetic field and the velocity. It's 90 degrees acting. And the magnetic force always acts 90 degrees to the velocity of the particle and the field. But notice what's going to happen. If this particle really was racing this way and encounters a magnetic field, it's now being pushed down. So what's going to happen is it's going to curve its path. And let's look at it at a different location. It curves its path and arcs it downward. So let's draw another position of this particle there. What is the velocity of the particle here? It's no longer traveling here. It's been forced to move this direction. And now let's ask ourselves, what's going to be the magnetic force at this point? All right, so the magnetic force goes into the board, but now the velocity of the particle is acting in the down direction. I go V cross B. Here are the vectors. If I cut into V, cutting into then B, then the magnetic force is pushing to the right. Magnetic force pushes to the right means there's a force now acting this way. Notice how the direction of the magnetic force totally changed. It changed because the direction of the particle velocity was different after it had moved a little bit. You can see what's going to happen. This force is going to then move this particle, and so now the particle is here and it's traveling this direction. And so now we can speed things up a little bit and say, all right, what happens here? We have magnetic field into the board. We have a velocity of the particle acting this direction, like this, and we go V cross B, Q V cross B. And then we have a force acting in the up direction. And I know now that you see the pattern, there's the magnetic force. And so once that magnetic force acts on the particle is going to move right here. And it's going to be traveling like this. And we'll do it one last time. We have the magnetic field going into the board. The particle velocity is now acting up. V cross B means we cut into red and then yellow. The force is acting now to the left. And so there's now a force acting this way. And what's that force going to do? It's going to curve the path of the particle so that it goes back to its starting point. No matter where on this path the particle is, if it's moving perpendicular to the magnetic field at all, then there's going to be a force always trying to push it to the center of the motion. And so it's going to orbit like this forever and ever and ever and ever and ever. The magnetic field is going to act almost like gravity, and it's going to pull it in, but it's not gravity, it's a magnetic force. It's governed by V cross B. But notice, there's a couple things I want to say. Notice that when the velocity of the particle is not perpendicular to the field, but parallel to the field like this, there is no magnetic force. We just talked about that. So there's no influence of the magnetic field. It can freely move left and right along the field lines, but it's only constrained to orbit in this direction. This is what I meant when I said that they're trapped along the field lines. They can freely move along the field because there is no magnetic force in that direction, but the orbiting motion comes from the constant inward force as the particle moves around. Last thing I'm going to say about this before we conclude is that the formula is QV cross B. So the Q here is the charge on the particle. All of these drawings were sort of pretending the charge was positive. Q, then V cross B. Q times V cross B. If I kind of implied that the charge was positive 1 here. If this were an electron, then this charge would be negative 1. And that means that whatever V cross B gave you from the right-hand rule, you would just stick a negative sign on the front. So what I'm trying to say is if this were an electron instead of a positive charge, then if it was moving this way, then there would be an upward force. And what that would do is it would cause it to orbit the opposite direction. Because as the electron got to this position, its velocity would be opposite of this one, so you would cross it again with the negative sign, you would get an inward force, and the electron would orbit in exactly the opposite fashion. So when you look at the plasma, or if you could look at the plasma, all of the positive charges are orbiting one direction, and all of the negative charges are orbiting in the opposite direction, but they're always orbiting. They're what we call trapped by the plasma. However, they can move along the field lines, no problem. So let's tie this back towards the aurora, and then we're going to conclude by talking a little bit about fusion and rocket engines. So let's go over here to this board. And let's sort of discuss what we have. If we have, you know, a XYZ coordinate axis, so this is like X, this is Y, and this is Z, right? If we had a uniform magnetic field, let's say, just like I had drawn originally, but in this case, I'm going to draw it to the right, right? I'll just draw it to the right like this. And I had a charge in that field, then what's basically going to happen, right, is the particle is going to orbit the magnetic field lines, but it can freely move downstream, but it's going to orbit the magnetic field line. So if you turn this on its end, where you're looking this direction, then the field is going away from you, just like it was here on the board going away from you. The orbiting motion was like this way, counterclockwise, right? And so if I was looking this way, it would be going like this, counterclockwise here, and the electrons would be going the other direction. Now, this is why they get trapped. But as we said, from our most basic drawings that we had, near the poles, everything is trapped, but what's going on here is the magnetic field, first of all, it's changing directions, and second of all, it's getting more concentrated as it gets to the poles. So let's try to draw a diagram of what the magnetic field might look like near the poles of the Earth. So near the poles of the Earth, they're going to be concentrated, but then around the equator, they're going to be less concentrated. So this is just a cartoon, all right? But you got to work with me here. So something like this. Notice how they're more concentrated near the poles. I'll just do it like this. Something like this. When the magnetic field is bunched up more, like here and here, we say it's a higher concentration of the field, whereas it's not so much here. Now, first things first, magnetic fields, they always have to form closed loops. I drew them like this, but that's really not correct. The magnetic field really has to come back and connect to the other side. Magnetic fields always form closed loops. So if you want to think of it this way, the magnetic field forms closed loops. I'm just drawing a profile so you can see near the poles, it's more concentrated, and near the equator, it's not. If we had a particle right here, which is at the equator of the Earth, let's say, these are the poles, this is the equator, and if this particle locally at this point, see how the magnetic field's curving, but locally you can consider it to be flat right here, okay? And let's say that the particle is traveling into the board, that's its velocity right there. So the magnetic field right here is locally flat, even though it is curved overall, and the velocity of this particle is traveling, let's say initially into the board, and it's a positive particle, if I can hold them, then it would be Q, V cross B. So I go into the V first, cross would B, and the force would act downward, right? So the magnetic force would then act downward. So here would be the force right here. We'll call it FB acting downward. All right? Now what's going to happen, the particle was traveling into the board, and it's going to be orbiting because the magnetic field is going to be acting downward. So as it goes into the board, the force is going to cause it to curve around and around and around like this. And so what's going to happen is that this magnetic force is going to cause a curved trajectory, which will be something like this. Maybe it'll go up and then down and then up and then down and then up and then down. You see, it's kind of confined. It's kind of, it can cut across. There's what we call a gyro radius. You can calculate it when you study the stuff in detail. There's a radius to the orbit that's very well defined. Right now, I'm drawing it not so great because this is just a freehand thing, but you get the idea. It's going into the board. There's a force down that causes it to be curved down. And so kind of like follow this helical trajectory right here. Here's the critical thing I really wanted to point out to you though. If you consider another point, maybe right here, as the magnetic field has taken a turn like this, locally the magnetic field is kind of like, I don't like using that color. Locally the magnetic field is curved down like this because it's changed direction, the magnetic field's changed direction. But remember, the velocity of the particle is still into the board. So if the magnetic field is now acting downward like this, and the velocity of the particle is still into the board, because what happened is it was spiraling here, now it got back to this point and is going into the board again, but the magnetic field is down, and this thing is traveling into the board like this, right? Then it's QV cross B. Look at what's happening. The field is now slanted, and the velocity is into the board. QV cross B means I have a thumb that's acting no longer, up here it was straight down, but down here it's at an angle. And as it curves more, it's going to be more at an angle. So what I'm trying to say is that right here, the magnetic force would be something like this. Notice how the magnetic force changed directions. Up here, it was straight up and down, causing the orbit to happen. But as the particle moved into the higher region of the field, the force is no longer straight down. It is a portion of the force is pushing back on the particle. And as the field gets more and more and more concentrated, this effect is more pronounced, right? So there might be a kickback force that looks even more horizontal like this. So this is the mechanism as to how the particles get trapped in the field and how they get kicked back at the poles. It's called magnetic confinement. If you make a magnetic region, we call it a magnetic bottle, and we make it in a lab. Then if you make a magnetic region which is very high at both ends, but not so high in the middle, then you can cause the plasma to be confined. And the reason it is confined is because, exactly as I went through it, with the QV cross B magnetic force is straight down here, no confinement, but once the magnetic field changes, then whenever you do the V cross B, then the force is now at an angle. So part of it is acting sort of in this direction, and part of it, you can think of it as kicking the particle back in towards the lower density region. The same exact thing is going to be happening over here. If you have a particle, let me see if I can do it with, yeah, here. If you have the particle that's been, after it's been kicked back over here, it gets to this part of the magnetic bottle. The magnetic field locally is right here. And then if the magnetic field's locally up like this, and the velocity of the particle, again, is still into the board, as we get to this region right here, we're saying the magnetic field spirals and the velocity is into the board. So you have a field up and you have a velocity into the board. Then you have a situation something like this. V cross B means I grab and I point this way. Where's my thumb pointing? It's pointing at an angle down, which means it's locally, the magnetic, I don't know why I put the B up here. I guess I'm a little excited. The magnetic force is at an angle this direction. Notice the magnetic force is always perpendicular to the field and the velocity of the particle. It's just that whenever the field changes direction over here and gets stronger, there's a portion of the magnetic force which tends to push it back in here. Once it passes through here and it gets over here, there's a portion of the force, magnetic force, that tends to push it back. So if the plasma ever gets here, it tends to move to the middle. But when it gets over here, it tends to move back to the middle. So yes, you have to have a very high field here. The stronger the field that you have on the ends, the better the plasma confinement. This is what is happening for the aurora. When the particles are spiraling around, they're getting to the poles, then there's a magnetic kickback force which is trying to push them magnetically away from the poles. But if randomly, through chance, there's a certain percentage of the plasma with a really high energy to overcome this kickback force and still collide with our atmosphere, producing the aurora. But most of the plasma just gets kicked back and ends up going all the way back to the other pole, kicked back over and over and over, just like inside of this magnetic bottle. And then the interactions with the gas is what causes the light show that we see that we call the aurora. So the entire concept of an aurora is the magnetic forces acting on the solar wind, which is a charged plasma, keeping it confined around the Earth, and then some percentage of them are able to get past the magnetic force, past the confinement through a high magnetic field, interact with our atmosphere, and make the light. Now I'll talk just for a second about a couple of applications of this. This whole thing that's happening is called magnetic confinement of plasma. It has a beautiful name. I love it. It makes you sound so smart. But all it means is you're trying to make the plasma stay in a certain region in a magnetic bottle. All you have to do is have an electromagnet on one end, an electromagnet on the other end, maybe a superconducting magnet if you want a really high magnetic field strength, and then the plasma will stay between. However, this kickback force is not 100%, so some amount of plasma will leak out. And maybe you want that. For fusion, you don't want that, but maybe if you're trying to make a rocket, you want that. Maybe what you do is you make one side really high field strength, and over here, maybe a little bit less field strength, so that the plasma is in here, it's being kicked out, and a small percentage of the plasma is allowed to escape very, very rapidly through an exhaust nozzle. You call it a magnetic nozzle. This is how one form of plasma propulsion works. It's not how all of them work. It's how the one I worked on works. You ionize a plasma, and you have it in this magnetic region, and then you use magnetic fields to let some of the plasma out, and when you let it out, it's at a really high energy, very high velocity coming out of the end, which pushes your spaceship. That's what you want, right? And there's a whole bunch of reasons as to why that's useful. Maybe I'll do another video on that one day. If you want to hear about that, please let me know. But it's kind of beyond the scope of this. What is the other purpose of magnetic confinement? One purpose: fusion research. The biggest fusion reactors that we have, test reactors, they all use magnetic confinement. The plasma that we make in the laboratory is too hot to hold it in like a stainless steel vessel. You have to have a magnetic field to squeeze it and to try to get the atoms to fuse. And the way we do that is by very specially shaped magnetic fields, usually not exactly in this configuration, but similar configurations, to confine the plasma and to squeeze it so that you can push the ions close enough together to achieve fusion. That's how they all work. So what we did in this lesson is we talked about something that I find fascinating: the northern lights, Aurora Borealis, the southern lights, Aurora Australis. And then we talked about how they happen. From a kind of a lower level point of view, the solar wind hits the magnetic field, it gets trapped, interacts with the gas in the atmosphere and makes photons of light, and we see them. That's fine. But then we went a little bit deeper. We said, all right, what's really happening is that the planet has this magnetic field here, and the particles are trapped because they're spiraling along the magnetic field lines, but when they hit the high magnetic field region, they get kicked back, and they basically go back and forth all the way around the planet every 4 or 5 seconds. Now notice, I didn't actually say it, but if you look closely at the pictures from space of Jupiter or Saturn, you'll see the aurora is more of an annulus than a flat surface. And that's because most of the interaction with the gases is happening in an annular ring. So this is the aurora is sort of like an annular phenomena, actually. And so that's why it's not exactly on top of the North Pole, because the magnetic field lines are coming in this annular region right there. And it can extend down in the lower latitudes depending on the intensity of the solar wind. The higher the intensity or the energy of the solar wind, then the more intense the aurora is, because the higher the solar wind energy, then the more chance the particles can have of getting past this magnetic kickback force and making it down into the lower atmosphere in order to ionize the gas and make the light. All right, so I'd like to know what you think. Please drop me a line. Let me know. Was it too much? Too little? I mean, I could have just said, hey, this is how it works. But the phenomena of magnetic confinement I find fascinating, because we will achieve nuclear fusion before my lifetime is over. I very firmly think, following the research carefully, plasma propulsion is already a thing. We use it a lot for satellites already. It's going to become an even bigger thing in the future. And so I thought tying the two together would be worthwhile. All right, follow me on and we'll learn together in the next one.